Hey guys, Mr. B here, and this video we're going to be going through the Chapter 12 review guide on stoichiometry. So I've got my desk cam set up. We're going to be doing our work here on paper. I've got our review sheet up so we can see the problems, but I'm going to do this on paper mainly because it's just faster, and that way I can also show formatting a bit better rather than having to type it out. So, all right, let's begin here with number 1. So it says problems A through C involve the balance equation below. So I'm going to write this on my paper just because we're going to need it. And of course, we can always look at it on our worksheet. But I figure if I have it on paper here, it'll be a little bit easier to deal with. So, all right, we have 2NaAl. I write too large also, which is a problem. Plus 3H2 gas. Okay, and I write too large. Anyway, all right, so here's our reaction. Part A. So it says, if 11 moles of aluminum are used, okay, so we're starting with 11 moles of aluminum, how many moles of H2O are needed to react with it? All right, so we're going from moles of aluminum to moles of H2O. To go from moles of one material to moles of another, we need to use the mole ratios and the reactions. So we're going from aluminum, which is 2 moles, to H2O, which is 6 moles. So it's a 2 to 6 ratio or a 1 to 3 ratio. So we're going to set up our conversion table like this. For every 2 moles of aluminum, we're going to put this on the bottom of our conversion because we're starting with moles of aluminum and we want that to cancel. And 6 moles of H2O is going to go on the top like this. Okay, that way moles of aluminum cancel and we get moles of H2O. And basically we're going to take 11, multiply by 6, divide by 2, or basically multiply by 3. So, and I get 33 moles of H2O is needed. All right, problem A done. Let's take a look at, oh, I apologize, hit the microphone there. Let's look at problem B. To make 14 moles of H2, how many moles of aluminum are needed? Okay, so they want us to determine how many moles of aluminum from 14 moles of H2. All right, so similar to the first problem, but now we're going from moles of H2 to moles of aluminum. This is a 3 to 2 ratio. Okay, so every 3 moles of H2, 2 moles of aluminum. Since we're starting with moles of H2, I want to put my 3 moles of H2 on the bottom, my 2 moles of aluminum on the top. The moles of H2 will cancel, and I'm going to take 14 times that by 2, divide by 3, and I get, oh, wrong color there, 9, I guess around a 2 sig figs, 9.3 moles of aluminum. All right, there is problem B done. All right, looking to problem C. If 1.75 moles of NaOH are used, how many grams of NaAlOH4 will be produced? Okay, so now we're going to be going from moles of one material to grams of a different material. All right, so this is going to require a few more steps, okay? But first thing is, we want to convert into moles if we're not already in moles. Okay, now in this problem, we are in moles. Okay, so first step is we're going to go from moles of this NaOH to moles of this NaAlOH4 using the mole ratios. Now the nice thing actually is looking at this, they are a 2 to 2 or a 1 to 1 ratio. So the number of moles of NaOH is actually the same number of moles of NaAlOH4 because they have the same ratio. So this number that we're starting with is also equal to 1.75 moles of NaAlOH4. And from there, since they want us to convert this into grams, we just have to find the molar mass of this material so we can convert to grams. So we are going to need a periodic table, which I realized I do not have on me at the moment. So I'm going to pull one up. I left mine upstairs, and that's my fault. Anyway, all right, so I'm looking at a periodic table on my computer here, but if you have yours in front of you, obviously use yours. So we have Na, which is 23 grams. We have aluminum, which is 27 grams. And I'm going to round to whole numbers here just to make it a little bit easier. Oxygen is 16 grams, but this 4 in parentheses is going to multiply that. So it's 4 OH, or 4 O's, okay? So 1 O here times 4. So we're going to multiply that by 4. So 16 times 4, we get 64 grams. And then lastly, we are going to take our H, which is 1 gram a piece. And again, this 4 is going to multiply that. So we're going to multiply that by 4 as well and get 4 grams. And then, of course, we're going to need to add all of these together to get our total. So 23 plus 27 plus 64 plus 4. Just going to make sure we do this right. So 23 plus 27 plus 64 plus 4. I get 118 grams per mole. All right, so here's our molar mass. And we are going to use this conversion factor to convert from moles to grams. Seeing as I'm starting in moles of NaAlOH4, the 1 mole is going to go on the bottom. The 118 grams is going to go on the top. That way moles will cancel. And we're basically going to take 1.75 times 118. And we get, and I guess if we round to whole numbers here, or 3 significant figures, 207 grams. Okay, I get 206.5, but again, rounding properly, 207 grams. All right, so there is our answer for that one. All right, letter D, last one. It says, if 30 grams of water are used, okay, so 30 grams of H2O, that's water, are used, how many moles of H2 can be produced? All right, so we're going to go from grams of H2O to moles of H2. All right, I'm going to kind of block this off so that way we know this is a whole different problem and we don't get this confused with this other math work we already have written down. Okay, so step 1, get into moles. Okay, seeing as we're starting in grams, our first step is we need to convert this into moles. Okay, so I'm going to set up a conversion here. My first step is to get this into moles. To do that, I'm going to need to know molar mass. So H2, so that's going to be 1 gram from the hydrogens times that by 2 because there are 2 of them. So that's 2 grams for the H's. Oxygen is 16 grams. Add those two together, and we're going to get a molar mass of about 18 grams per mole for water. Okay, so there's our molar mass. So this is the first conversion we're going to use. We got to get these grams of H2O into moles of H2O. Okay, so grams to moles. Since I'm starting with 30 grams, my 18 grams of H2O will be on the bottom. My 1 mole of H2O will be on the top. Okay, like this. So my grams of H2O are going to cancel. Now, I could solve this and get an answer and write it down and then do the next part, but I'm just going to do it in one long conversion. So if we do this math out, we're going to get a number, and the units on that number are going to be in moles of H2O. Okay. Now letter D is asking for moles of H2. So now that we've done this first step, we will have moles of H2O. If we want to go from moles of H2O to moles of H2, we need to look at the mole ratios in the reaction. It's a 6-to-2 ratio. Every 6 moles of H2O, we will make 3 moles of H2. So I'm going to set up that conversion factor here in the next part of my problem, because that will convert moles of H2O into moles of H2. Okay, so since I have moles of H2O here, 6 moles of H2O are going to be on the bottom, and the 3 moles of H2 will be on the top, okay, like this. So moles of H2 will cancel. And so now if I do this whole thing out in just one long go, and I'll put my calculator here so you can see all the math work. we're going to take 30, divide by 18 equals, times 3 equals, and divide by 6 equals. And I get, as an answer, 0.833 repeating. And if we round to 3 significant figures, we'll get 0.833 moles of H2 as our answer. Okay, so 0.833 moles of H2 can be produced. All right, so that is problem number 1, letters A through D. Hopefully that makes sense after all the practice we've done for this whole chapter up to this point. But let's move on to problem number 2. All right. So problem number 2. Let's scroll down here. So it says balance the following equation. All right, so we have FeS2 solid plus O2 gas makes Fe2O3 solid plus SO2 gas. Okay, so here is our equation, and it says balance this. All right, so first thing we got to do is balance. Now, this chapter wasn't really on writing chemical equations and balancing, so hopefully you remember how to do this from chapter 11. But real quickly, let's just take a look and try to balance this. I'm going to do this, I guess, in pencil. So that way, if my numbers are wrong, I can erase them. I don't want to write them in pen and then have to make some changes and I can't erase it. So, all right, so starting off, just at the beginning, we have 1 iron here and 2 irons there. So I can already see the irons are not balanced. Let's just put a 2 here in front to balance those. And then let's balance the sulfurs next. So there's 2 irons there, 2 irons there. 2 times 2, so that's 4 sulfurs. Okay, 2 times 2, that's 4. Here we only have 1, so let's put a 4 there to try to balance out the sulfurs. And then for oxygens, we have 4 times 2, so that is 8 oxygens there, plus the 3 that we have there. So that is a total of 11 oxygens on this side. And on the left, we only have 2. All right, so to do this, I'm going to use my little half number trick, okay? So if I want to go from 2 oxygens to 11, I'm going to have to multiply this by a non-whole number. 5.5, okay, 5.5. 5.5 times 2 gets me 11. Okay, now I can't leave it this way, but this is a start. So if this is 5.5, that gives me 11 oxygens. And let's just make sure everything is balanced. So we have 2 irons here, 2 irons there. 2 times 2 is 4 sulfurs. 4 times 1 is 4 sulfurs. Then oxygens, we have 5.5 times 2, that's 11. This is 3 plus 4 times 2 is 8, and that's 11. All right, so everything is balanced. So from here, to get a balanced reaction that does not involve a half number, we're just going to double all of our coefficients, and that will give us our proper balanced equation with full whole numbers and everything. So the 2 is going to change to become a 4. Okay, so we're going to double that. So that's now a 4. The 5.5, if we double that, that is going to become 11. This technically was a 1, but if we're doubling it, it's now going to be a 2. And this 4, if we double that, that's going to become an 8. So this is going to be an 8. And then from there, we have a fully balanced equation. All right, so let's move on then to letter A. If you start with 64 grams of O2, okay, so 64 grams of O2, how many grams of SO2 can be made? All right, so over here, we're going to end in grams of SO2. Okay, so step 1 is always going to be to convert to moles if we're not given moles already. This, of course, is not in moles. So step 1, let's convert our grams of O2 into moles of O2. To do that, we're going to need the molar mass of O2. Okay, so O2 is 16 grams for oxygen, times that by 2. That's going to give us 32 grams of O2 per 1 mole of O2. Okay, so there's our molar mass. So this is going to be our first conversion to convert grams of O2 into moles of O2. Since we're starting with 64 grams, the 32 grams of O2 will go on the bottom. 1 mole of O2 will go on the top. That way our grams of O2 cancel. Okay, so this is going to get us into moles of O2. I'm going to do this in one big conversion again, just so I don't need to like pull my calculator up and do all these calculations as I'm doing the problem. I'll just do it all at the end. So, okay, so this will get us into moles of O2. Now that we're in moles of O2, if we want to go from moles of O2 to moles of SO2, okay, because this is the material we're trying to get into is SO2. So to do that, we're going to need to use the ratios in the reaction. So we have moles of O2, so 11 moles of O2 to 8 moles of SO2. Okay, so it's an 11 to 8 ratio. So the next conversion here is going to convert moles of O2 into moles of SO2. Since I'm starting with moles of O2 here, my 11 moles of O2 will be on the bottom, and my 8 moles of SO2 will be on the top. And again, I'm getting this ratio, okay, this conversion factor, 11 moles to 8 moles, right here from the reaction. Okay, again, if it's properly balanced, which it should be. So those will cancel. And now I'm in moles of SO2, and I need to get to grams of SO2. So just like in the first step when we converted from grams to moles, now we're going from moles back to grams. We will need molar mass for this. So let's calculate it. Sulfur has a molar mass of 32 grams. Oxygen, or O2, we know also is 32 grams because we have it right over here. So adding these together, this is a molar mass of 64 grams of SO2 per 1 mole of SO2. Okay, so here's our molar mass. Since we're starting with moles of SO2 here, the 1 mole of SO2 will go on the bottom of our fraction, and the 64 grams of SO2 will go on the top of our fraction. So that way moles of SO2 cancel out, and we will then be in grams of SO2. All right, so this is all the math work we need to do. Again, I set it up in one long conversion just to make it simpler, and I didn't need to do all these calculations, as I'm doing the problem. So let's do it all at the end. So we're going to start with 64 grams of O2. Okay, so 64. Divide by 32. So divide by 32 equals times 8. Divide by 11 times 64. And I get, and if we round to two significant figures, this 93.09 whatever is just going to be 93 grams. Okay, that would be our answer, rounded to two significant figures. And rounded to two sig figs because this 64 had two sig figs. All right, so there is our answer there for letter A. Moving on to letter B. If we start with 100 grams of Fe2, or I'm sorry, of FeS2, how many grams of Fe2O3 can be made? Okay, so this problem is just like the first one, but we are starting with a different material, but it's in grams, and we're converting to a different material, but it's still in grams. So same steps are going to apply. Step 1, convert to moles. Step 2, go from moles of one material to moles of the other material using your molar ratios. And then step 3, convert back to grams. Okay, so let's set this up. First part, we will need to know molar mass, so we can convert this into grams. So iron, again, I'm using a periodic table on my computer because my paper one is upstairs, and that is my fault. So iron, we're just going to round to 56 grams for the iron. Sulfur is 32 grams. We're going to times that by 2 because there are 2 of them here in this compound. So that is 64 grams. And then if we add those together, 56 plus 64, I get 120 grams of FeS2 per 1 mole of FeS2. Okay, so there's our molar mass. So let's use this first conversion. Since we're starting in grams of FeS2, the 120 grams will go on the bottom, like this. 1 mole will go on the top. Okay, so grams will cancel. Okay, once we get to this point, we're now in moles of iron 2, or iron sulfide, I guess. And we're going to go from this material to this material. So we're going to need to use our mole ratios. It's a 4:2 ratio. So for every 4 moles of FeS2, we will make 2 moles of Fe2O3. So since we're starting with moles of FeS2 here, the 4 moles of FeS2 will go on the bottom. The 2 moles of Fe2O3 will go on the top, okay, like this. Oh, and I did not write moles. I apologize. Moles of Fe2O3 and moles of FeS2. I really want to make sure we write those units so that we can see that they are canceling, okay? So moles of FeS2, moles of FeS2. This will get us into moles of Fe2O3, and then the last part is to get that into grams of Fe2O3. So to do that, we will need to know molar mass of this material. So let's calculate it here real quick. Fe, and there's 2 of them, so this is going to be 56 grams. Okay, we have that from right here. Times that by 2 though, because there are 2 of them. So 56 times 2, I get 112 grams. And then the oxygens, there are 3 of them. Oxygen is 16 grams, times that by 3. So 16 times 3 is 48 grams. And then, of course, add those together. And I get a molar mass of 160 grams of Fe2O3 per 1 mole of Fe2O3. Okay. So here is our molar mass. We're starting with moles of Fe2O3 here. So if we want to convert from moles to grams, the 1 mole of Fe2O3 needs to be on the bottom of our fraction here. And the 160 grams of Fe2O3 needs to be on the top of our fraction like this. So moles cancel out with moles. And then we can do our math work. So we're going to start with 100. We are going to divide that by 120. 100 divided by 120 equals. All right. Then we're going to times that by 2 equals. Divide that by 4 equals, and then times by 160 equals. And I get 66.6. Technically, this is 1 significant figure, but we're just going to count it as 3 in this case. So let's just say 66.7 grams is our proper answer. Okay, 66.7 grams. All right. So there we go. There is problem number 2, all done, A and B. Let's move on to problem number 3. Got a new piece of paper here. All right. So problem 3. It says, write the balanced chemical equation for the following reaction and use your ability to predict the amount of product that should be made to calculate percent yield. All right, so it says calcium carbonate decomposes to produce calcium oxide and carbon dioxide. If 25.4 grams of calcium carbonate react to produce 13.2 grams of calcium oxide, what is the percent yield for the reaction? All right, so for this problem, there's going to be a few different things to do, but the main thing to begin with is we have to write out the chemical reaction because they're not giving it to us. So, well, they're telling it to us, but they're not giving us any chemical formulas. So it says calcium carbonate decomposes. All right, so the chemical formula for calcium carbonate is CaCO3. Okay, now I'm not going to go into how do we write chemical formulas. We did that in chapter 9, in chapter 10, chapter 11. At this point, you should be able to write a chemical formula. But if not, go back and look at some past videos, I suppose, or reach out to me and we can do some work together. So calcium carbonate decomposes to produce. Okay, so it's decomposing. There's only one reactant. We're producing calcium oxide. So calcium oxide has a chemical formula of CaO. And carbon dioxide, that has a chemical formula of CO2. Okay, so here are our products. And it says if 25.4 grams of calcium carbonate, okay, so we have 25.4 grams of calcium carbonate. So 25.4 grams of calcium carbonate react to produce 13.2 grams of calcium oxide. So 13.2 grams of calcium oxide here. What is the percent yield for the reaction? All right, so this problem might sound kind of challenging because we might not really know, like, what are we supposed to do? Again, let me explain what the problem's actually asking. So this problem basically is saying if you start with this much calcium carbonate, in real life, this is how much stuff someone is making. However, this number that they're giving us here for this calcium oxide may not be the amount that we could make. We could make more. So this number that they're giving here is an actual yield. Okay, this is an actual yield. We need to calculate a theoretical yield. Okay, a theoretical yield is how much should you be able to make based on calculations. And then once we have a theoretical yield, we can compare it to the actual yield to then get a percent yield. So basically what we're going to do in this problem is we are going to start with 25.4 grams of calcium carbonate, and we are going to calculate how many grams of calcium oxide should we be able to make. Then we'll compare it to the number they're giving to us in the problem. So over here, we're going to end up in grams of calcium oxide. And we're just going to do a conversion. And this problem is going to be very similar to the previous ones we just did. So step one is get into moles. Okay, we are in grams of calcium carbonate. We need to get into moles of calcium carbonate. So to go from grams to moles, we are going to need to use molar mass. Again, I'm going to pull up a periodic table to make sure that I have these numbers correct. So molar mass for calcium carbonate. We have a calcium, that's 40 grams. We have a carbon, that is 12 grams. And we have 3 oxygens, so that's 16 grams, and then times that by 3 because there are 3 of them. So let's go 16 times 3. And I get 48 grams for the oxygens. Then, of course, we will need to add all these together. So 48 plus 12 plus 40. We get a nice even 100 grams of calcium carbonate per 1 mole of calcium carbonate. So there's our molar mass for that material. So we can use this now to convert from grams to moles. Since we're starting with grams of calcium carbonate, the 100 grams of calcium carbonate will go on the bottom of our fraction. The 1 mole of calcium carbonate will go on the top of our fraction like this. So grams will cancel. This is going to get us into moles of calcium carbonate. Then we want to go from moles of calcium carbonate to moles of calcium oxide. Okay, so we are going to look at the mole ratios. Now I just realized, by the way, and this is my fault, but I realized that we never looked to check to see if this was balanced. We just wrote out the chemical formulas. So let's actually check this real quick to make sure it is balanced. I actually think it is, but we'll double check. So we have 1 calcium and 1 calcium, 1 carbon and 1 carbon, 3 oxygens, and then 1 plus 2 is 3. Okay, so this is actually already balanced. Lucky for us. I should have done that in the beginning, and I didn't, so I apologize if you caught it, and I didn't realize till now. Good job. So everything is reacting in a 1-to-1-to-1 ratio, which means that this next step, to go from moles of calcium carbonate to moles of calcium oxide, we really don't need to do it because it's going to be the same number. Okay, it's a 1-to-1 ratio. So basically for every 1 mole of calcium carbonate, we're going to make 1 mole of calcium oxide. Okay, 1-to-1. And we're setting it up this way so that way moles of calcium oxide cancel with moles of calcium oxide. Then the last part, of course, is to get this into grams so that we can compare it with the grams that were being given at the beginning of the problem. So to go from moles of calcium oxide to grams of calcium oxide, we're going to need to use molar mass, just like we did before. Okay, so we know that calcium is 40 grams because we have it right here, and oxygen is 16 grams because, again, we have that right there. So we're just going to add these together to get our molar mass for calcium oxide. So 40 plus 16, we get a molar mass of 56 grams of calcium oxide per 1 mole of calcium oxide. Like this. since we're starting with moles of calcium oxide, the 1 mole of calcium oxide is going to be on the bottom. The 56 grams of calcium oxide is going to be on the top. That way moles of calcium oxide cancel. And this then will get us a theoretical yield. Okay, so this answer that we're about to get is our theoretical yield. This is based on calculations, how much should we be able to make? Then we'll compare it to the actual yield up here. All right, so on our calculator, here we go. We're going to take 25.4, divide that by 100 equals, times that by 1, divide by 1. Okay, so same thing, and then times this by 56. And we get, and we'll round to 3 significant figures, 14.2 grams of calcium oxide. Okay, so this is our theoretical yield. So in theory, basically, this is how much we should be able to make. But in the problem, they're telling us we're only making 13.2 grams. So now we need to determine what our percent yield is. Okay, it's basically like how far off are we? So just to remind you, percent yield is actual yield divided by theoretical yield times 100. Okay, this is our equation. So I guess we'll do the math in a different color up here. But our actual yield is 13.2 grams. Our theoretical yield was 14.2 grams. Times it by 100. Let's see what we get. So 13.2 divided by 14.2 equals times 100. And rounding to 3 significant figures, we would get 92.9. The 5 would round it up to a 10, which would round the whole thing up to 93.0%. Okay, this is our percent yield, 93%. Which, again, you're always striving to get 100% yield, but typically you'll never get 100% yield. But 93% is pretty good. So, all right, there's problem number 3. Let's move on to problem number 4, and these problems on limiting reagents or limiting reactants. Okay. So it says at high temperatures, sulfur combines with iron to form the brown-black iron 2 sulfide. In one experiment, 7.62 grams of iron are allowed to react with 8.67 grams of S8. What is the limiting reagent and what is the reactant in excess? Okay, so let's write out our reaction here on our paper first, just so again that we have it. Oh, there we go. Wrong symbol. All right. So here's our reaction. And first thing I notice, and if you didn't notice this, that's okay, I guess. But first thing is, it's not balanced. We have 8 sulfurs here, and we only have 1 there. So we are going to have to balance this reaction, but it's pretty quick to balance, I think. We're just going to put an 8 here, which will give us 8 sulfurs, and then that gives us 8 irons, so we'll need to put an 8 there as well. All right. So now that it is balanced, for part 1, or letter A, we have 7.62 grams of iron, and we have 8.67 grams of sulfur, and they want us to tell them which one is limiting. All right, so if we're doing a limiting reactant problem, the first thing is to know that this is the material that we are being given. Okay, so what we're going to do is, this is what we're being given. We need to figure out how much we need to react with this. Okay, so the first part, as always, is going to be to get into moles. Okay, so let's convert both of these into moles. The first one, of course, 7.62 grams of iron. We're going to convert this into moles of iron. To convert into moles from grams, we'll need to use molar mass. If we look on the periodic table and find the molar mass of iron, it is 56 grams per mole. And because we are starting with grams of iron here, I'm going to put the 56 grams on the bottom, 1 mole of iron on the top. So that way the grams of iron cancel. Okay, so real quick, let's just pull out our calculator here. And we will take, sorry, my paper's sliding all over the place here. We are going to take 7.62 divided by 56 equals, all right, and I guess we'll round to 3 significant figures. So we'll get 0.136 moles of iron, okay? So again, this is still what we are being given in the problem. We just took what we are given in grams and converted it into moles. Same thing now, let's do that with the sulfur. Now it is S8, okay? It's not just S. So sulfur has a molar mass of 32 grams. But since there are 8 of them, we have to times that by 8. So 32 times that by 8, I get 256 grams per mole. All right, so here's our molar mass. Since we're starting with grams of S8, the 256 grams of S8 will be on the bottom. 1 mole of S8 will be on the top. That way grams of S8 cancel. So we're going to take 8.67 and divide this by 256 equals, and again we'll round to 3 significant figures, so 0.033, and that 8 is going to round up to a 9. Okay, so here's our moles of S8. Now again, this is still what we are being given. Okay, this is what we're starting with. To determine which one is limiting, we need to then think about it this way. If we are being given 7.62 grams of iron, or 0.136 moles of iron, how many moles of sulfur do we need to react with this? Okay, so we're basically going to go from moles of iron to moles of sulfur, and then we'll do the other way around here, and then we're going to compare, okay, so we can figure out which one's limiting. So the next part here is to go from moles of iron to moles of sulfur, okay, because we're being given this much iron, and I want to know how much sulfur do we need to react with this much iron. So in this reaction, it is an 8-to-1 ratio. So for every 8 moles of iron, we need 1 mole of S8. Okay, so moles of iron will cancel, and we'll get moles of sulfur, and it's going to be a really small number. So 0.136, and divide that by 8, and we get 0.017, and just to make it 3 significant figures, we'll add a 0 on at the end there, moles of S8. All right, so this is what we need. Okay, so if we're being given this much iron, we need this much sulfur to react with it. All right, let's go do the other one too, and then we'll compare just to make sure that we have all of the information we can. All right, so we're going to do the same exact thing down here. The ratio is still going to be 8-to-1, but since we're starting with moles of S8, that 1 mole of S8 is going to be on the bottom, and the 8 moles of Fe will be on the top, okay, like this. So moles of S8 will cancel. So we'll take 0.0339 times that by 8, and I get 0.271, and we're going to round to 3 significant figures, moles of Fe. Okay, now again, this is what we need to react with all of this sulfur. So from here, now we're going to compare, okay? So if I'm being given 0.136 moles of iron, I need 0.170 moles of sulfur to react with it. So let's look at what we're being given down here. Okay, we're going to compare. So I need 0.0170, and I have 0.0339. So I definitely have enough sulfur. Okay, if the decimals are confusing you, think of it as 170 versus 339, right? I need 170 moles of sulfur, and I have 339 moles. I have plenty. If we look at the other way around, if I need this much iron to react with all the sulfur, okay, so 0.271, and I only being given 0.136, I do not have enough, which means that iron is going to be the limiting reactant. Okay, so iron is limiting. And if iron is limiting, that means then that the S8 is excess. So here is our answer for problem 4, letter A. Okay, Fe is limiting, S8 is excess. So letter B now says, calculate the mass of FeS formed. So now the next part is asking, all right, now that you figured out which one is limiting, how much of this product then can you make? Okay, so basically all we're going to do is we're going to start with whatever material was limiting. In this case, it's the iron. Okay, so this 7.62 grams of iron, that's what we're going to start with. We're going to convert from grams of iron into grams of this FeS. Now we already did the mole conversion here. Okay, we went from grams of iron to moles of iron. That's step 1. We already have that. So we can just basically start with this number right here because we have to do that math anyway, and we've already done it. So 0.136 moles of iron. Now we're going to go from moles of iron to moles of FeS. Okay, we're going to go from moles of iron to moles of FeS because they want us to find the mass of FeS that is forming. And you'll see here, it's an 8-to-8 ratio, or basically it's a 1-to-1 ratio. So we actually don't even need to do any math for this because they're going to be the same number. So, I mean, we can write it out anyway, but there's really no point to because we're basically just going to have the same exact number times 8 divided by 8. So basically going to get 0.136 moles of FeS. That's how much product we can make in moles. And then, of course, they do want us to probably get this into grams because it does say calculate the mass formed. So the last part is just going to take this 0.136 moles of FeS and convert this into grams of FeS. And, of course, to do that, we are going to need to know molar mass for FeS, which we have the molar masses of iron and sulfur right here. So molar mass, we have Fe, which is 56 grams, S, which is 32 grams. Add these together, 56 plus 32. I get 88 grams per mole. So 88 grams of FeS per 1 mole of FeS. So there's our molar mass. All right. Since we're starting with moles of FeS, the 1 mole of FeS will be on the bottom, and the 88 grams of FeS will be on the top, so that those cancel like this. And then on our calculator, we will take 0.136 times that by 88 equals, and we get 11.968. And let's round this to 3 significant figures. So 11.9, the 6 would round that up to a 10, which would round this whole thing up to 12.0 grams of iron 2 sulfide can be made. Okay, so there is our answer for number 4, letter B. All right, I hope so far that you are sticking with me and you're understanding. We got a few problems left here to do. I know it's a longer video, but the whole point of this, of course, is to go over these problems and make sure we understand what we're doing. All right, number 5. Calculate the percent yield for an experiment in which 5.50 grams of SOCl2 was obtained in a reaction of 5.80 grams of SO2 with excess PCl5. Use the following equation. All right, so let's write the equation out just so we have it on our paper. PCl5 liquid makes SOCl2 liquid plus POCl3 liquid. Okay. So first thing is we should probably check to make sure that everything is balanced. Okay, it might be, it might not be. So real quick, let's see. 1 sulfur here, 1 sulfur there. 2 oxygens here. We have 2 oxygens. Okay. 1 phosphorus, 5 chlorines, 2 plus 3 is 5. Okay, so everything is already balanced. So that makes things a lot easier. So they want us to find percent yield. They're telling us that we are making 5.50 grams of this material. And we are starting with 5.80 grams of this material. Okay, so the way it's worded, it kind of is confusing. However, if we write out the reaction and we kind of write out our numbers like this, we can see where they are attached to. It makes it a little bit easier to see. Okay, so basically what they're saying is we are starting with this much SO2. And in the lab, someone did this and actually made this much SOCl2. Okay, so this is an actual yield. They want us to find percent yield. So we've done a problem like this already. Basically what we're going to do is we're going to take grams of SO2. We're going to calculate how many grams of this we should be able to make. And then we're going to compare it to the number they're giving to us in the problem to find our percent yield. Okay, so we're going to start with 5.80 grams of SO2. Step one, as always, is to convert that into moles of SO2. So sulfur, we'll need no molar mass. Sulfur is 32 grams. Again, I'm looking at a periodic table on my computer. You should look on yours on paper. Oxygen is 16 grams, but there's 2 of them, so you got to times that by 2. So that's 32 grams from that. Add those together, and we get a molar mass of 64 grams of SO2 per 1 mole of SO2. All right, so there's our molar mass. So let's convert this first from grams of SO2 to moles of SO2. Since we're starting with grams of SO2, I'll have the 64 grams of SO2 here on the bottom, the 1 mole of SO2 on the top, okay, like this. So my grams of SO2 will cancel. I guess I'm going to do these calculations rather than do it in one big long one. So 5.80, divide this by 64. We get, and we'll round to 3 significant figures. So 0, 9, 0, 6. The 2 will keep the 6 as 6. So we'll have something like this. Okay, so here's our moles of SO2. Then from here, we want to go from moles of SO2 to moles of SOCl2. Now, since everything is a 1-to-1-to-1 ratio, I don't really need to do any math for this because the amount of moles of this material will be the same amount of moles of this. So basically, we can just say this is going to be equal to 0.0906 moles of SOCl2. Okay, so these are just going to be the same. I don't really need to do any math. All right, so then from here, we want to convert this into grams of SOCl2 so we can compare it with the grams that we were being given in the problem. So next part here is 0.0906 moles of SOCl2. We're going to convert this into grams of SOCl2. We will need to know molar mass to do that. So sulfur is 32 grams. 1 oxygen, that's 16 grams. Then we have 2 chlorines, and chlorine is 35.45 grams, and we're going to times that by 2, because there are 2 of them. So 35.45 times that by 2, and I get 70.9 grams. All right, so let's then add all those together. So 70.9 plus 16 plus 32, I get 118.9. So 118.9 grams of SOCl2 per 1 mole of SOCl2. There's our molar mass. So we're starting with moles, which means the 1 mole of SOCl2 will be on the bottom of our fraction. And the grams, which is 118.9 grams, will be on the top of our fraction like this. Moles will cancel, and we will get grams. So let's take 0.0906 times 118.9 equals and we get 10.77 whatever. We're going to round to 3 significant figures. So 10.7 grams. Now again, this answer that we just got, this is our theoretical yield. Okay, so this is in theory, or based on calculations, this is how much we should be able to make. However, they're telling us that we're only making 5.50 grams. Okay, this is way less. So our percent yield then is what? All right, so for percent yield, we are going to take our, again, percent yield is actual over theoretical times 100. Okay, so our actual yield is 5.50 grams. So 5.50 grams of SOCl2. Our actual yield was 10.7 grams. So divide those two, times this by 100, and we're going to get a percentage. So 5.50 divide by 10.7 times 100, and we get, rounding to 3 significant figures, 51.4%, which is not a very good percent yield. Again, you want to get as close to 100 as you can, and that is not very close. So, all right, last set of problems. I know this has been a long video, and again, I appreciate you taking the time to stick it out with me and make sure that you know what you're doing and watching. Okay, so let's get through this last one. Here we go. When iron 2 hydroxide is mixed with phosphoric acid, iron 2 phosphate precipitate results. Balance the following equation. All right, so step one, we're just going to balance this equation. That's, I think, pretty simple. So let's write it here. So FeOH2, which is aqueous, reacts with H3PO4, which is aqueous. We're making Fe3PO4, solid, and H2O, liquid. All right, so there's our reaction. We have to balance this. So let's just start at the beginning again. I'm gonna do this in pencil just so that way if I need to change any numbers, I can change them. So let's just see here at the beginning, we have 1 iron. Here we have 3. So let's put a 3 there. Okay, that'll balance out the irons. That also is going to multiply this OH by 3. So 3 times 2, this gives us 6 OHs. Okay, now this is H2O written over here, but if we rewrite this as HOH, we can see that we only have 1 OH here, okay, versus the 6. So we need to put a 6 in front of this whole thing. That'll give us 6 OHs. Okay, so 6 OHs. Let's just start writing to keep track better. That'll also give us 6 hydrogens, so 6 regular H's. And over here we only have 3, so we'll put a 2 there. Okay, that will multiply the 3, so that'll give us 6. And that also is going to give us 2 PO4s, okay, 2 phosphates, which here we actually have 2 phosphates. So it looks like everything now is balanced. All right, so there we go. So to balance this out, here are our numbers. Let's just erase all this scratch work here, and I'll rewrite our numbers in red so that they stand out a bit. So again, let's just get rid of all this. Okay, so balanced numbers, we have 3, 3, 2, 1, which we're not going to write, and a 6. Okay, so 3, 2, 1, 6. All right, so that was part A, which was just balancing. Part B. If 3.20 grams of FeOH2 is treated with 2.50 grams of phosphoric acid, what is the limiting reagent? What is the reactant in excess? Okay, so a limiting reactant problem. So here we go. So we have 3.20 grams of FeOH2, and we have 2.50 grams of phosphoric acid, which is the H3PO4. All right. Again, this is what we are being given to begin with. Okay, so step one, again, as always, is convert to moles. So 3.20 grams of this material, we got to convert this into moles. To do that, we're going to need to know molar mass. Same thing with this, we got to convert this into moles. To do that, we're going to need to know molar mass. So moles of FeOH2 and moles of H3PO4. All right, so molar mass for FeOH2. So iron is 56 grams. Then we have this 2, which is going to multiply the O and the H's. So we're going to have 2 O's. That's 16 grams apiece, times that by 2. So that's 32 grams. And then the H's, which are 1 gram apiece, times that by 2. That's 2 grams. So we're going to have these numbers that we need to add together. So 56 plus 32 plus 2. So 56 plus 32 plus 2. And we get 90 grams for the FeOH2 per 1 mole of FeOH2. Okay, so there's our molar mass. Since we're starting in grams here, the 90 grams is going to go on the bottom. The 1 mole will go on the top. Okay, like so. That way grams cancel. All right, let's real quickly get our answer for that one. So 3.20 divide that by 90 equals. And rounding to 3 significant figures, we're going to get 0.356. So 0.356 moles. All right. Then for this one, let's find this molar mass. H3. So H, that's 1 gram. Times that by 3. So that is 3 grams for the H's. Phosphorus, I got to look this one up. I don't remember this one off the top of my head. We have 30.9, so we're just going to say 31 for the phosphorus. So 31 grams for phosphorus. And then oxygen, we have O4. So that's 16 grams times that by 4. 16 times 4 is, let's make sure I do that right. 16 times 4 is 64 grams. Okay. And we're going to add all those together. So we get 64 plus 31 plus 3. And I get 98 grams of H3PO4 per 1 mole of H3PO4. Okay. Since I'm starting with grams of H3PO4, the 98 grams of H3PO4 will go on the bottom. The 1 mole of H3PO4 will go on the top. So grams will cancel. Let's do the math out on our calculator here. So 2.50 divide by 98. And then rounding to 3 significant figures, we're going to get 0.0255. There we go. Okay. So there are our moles. Now again, this is what we are being given. Okay, all we did was just convert our grams into moles. Okay, that's it. We haven't done anything else. We just converted grams into moles. This is what we're being given. To do this and figure out which one is limiting, we got to figure out which one, how much we need of the other one. So if we're being given 0.356 moles of FeOH2, how many moles of H3PO4 do we need to react with all of that? So we can compare it with how much we're being given here. So to do that, we are of course going to go from moles of FeOH2 to moles of H3PO4. It is a 3:2 ratio, so we're going to need to use those numbers from the equation or the reaction. So for every 3 moles of FeOH2, we are going to have 2 moles of H3PO4, okay, like so. So moles of FeOH2 will cancel with moles of FeOH2. So 0.356 times 2 divided by 3 Rounding 3 significant figures, we're going to get 0.237 moles of H3PO4. And this, again, is what we need. Okay, so if we're being given this many moles of FeOH2, we need this many moles of H3PO4 to react with all of it. Okay, now, just for the sake of time, rather than doing this whole one out too, we already have all the information we need. So let's just take a look. So if we need 0.237, we only have 0.0255. So that is not even close, right? Like, we need 0.2, and we only have 0.02. So H3PO4 is definitely going to be limiting. Okay? So H3PO4 is limiting. And if H3PO4 is limiting, then that means that the FeOH2 is in excess. Okay. Now in the previous ones, I know that I did this math out as well, but we technically don't need to, because once you've done the first math workout, you can compare it with your other number, and then you're good. Okay. I just did both out before just to show you, but we technically don't need to. So, all right. So there is our answer for letter B. Letter C then, it says how many grams of Fe3PO42 precipitate can be formed. So basically now we're going to start with our limiting reactant, which is the H3PO4, okay, which is this material given here, and we're gonna calculate how much of this product can we make if we're starting with this much reactant. So we're gonna go from grams of this material to grams of that material, and that's it. Okay, now we've already done the first part, which is converting to moles. So I am going to get a new piece of paper, obviously, here because I write too large. So let's just move this over. We're going to rewrite our reaction here real quick too, so we still have it on our paper, even though I guess it's on the worksheet sort of, but it's not balanced. So 2H3PO4. I'm going to forget the whole aqueous stuff because like it doesn't really matter. It doesn't have any effect on our calculations, and just to save some time. So 6H2O. Okay, so here's our reaction. Again, for part C, they want us to calculate how much of this can we make. So we're being given, again, we're just going to use our numbers we've already used. Okay, so we're going to start with our limiting reactant, which was the 2.50 grams of H3PO4. First step is to calculate into moles, which we've already done. So we're just going to basically start with this number of moles already because we already have it. So 0.0255 moles of H3PO4. Okay, so there's our moles, and we're going to go from moles of this material to moles of that material. It's a 2-to-1 ratio. So let's set up our conversion table. So we're going to end in moles of Fe3PO4 2, and for every 2 moles of this H3PO4, we are going to make 1 mole of Fe3PO4 2. Okay, so it's again, it is a 2-to-1 ratio. Since we're starting with moles of H3PO4, the 2 moles is going to go on the bottom, so we can cancel those units out. So we'll take our calculator here, so 0.0255, and just divide that by 2 equals, so we get 0.0128, okay, again, if we round to 3 significant figures, 0.0128, and then we need to get this into grams, because they are asking for grams. So we'll take this 0.0128 moles of Fe3PO4 2, and we're going to convert this into grams. And to do that, we're going to need to know the molar mass of this material, and I'm sure it's actually a pretty large number. So here we go. So Fe, and we have 3 of them. Okay, so that's 56 grams times up by 3. Okay, so on my calculator, 56 times 3, that is 168 grams for the iron. then this 2 outside the parentheses is going to multiply the p's. So we have 2 p's. Okay, so 2 p's. And again, just to double check, so I don't remember phosphorus off the top of my head, it is 31 grams a piece. Times that by 2. So 31 times 2. We get 62 grams. And then this 2 is going to multiply the 4 oxygens. So we're going to have 8 oxygens total. Okay, so 16 grams for oxygen times that by 8. So 16 times 8. And I get 128 grams. And then, of course, we need to add all of those together to get our molar mass. So 168 plus 62 plus 128 equals 358 grams per mole, which, again, I knew that this is going to be a big number, so that makes sense. All right, so here is our conversion factor. Here's my moles of the material. So the 1 mole in our molar mass is going to go on the bottom, and the 358 grams will go on the top. That way moles cancel with moles. And we will take 0.0128 times 358 equals, and again, rounding to 3 significant figures, we get 4.58 grams can be made. There is our answer. All right. I believe there's one problem left. Here we go. So it says if 3.99 grams of Fe3PO4 is actually obtained, what is the percent yield? Okay. So we actually don't really need to do a whole lot of work here because we already did all the work. So this is a pretty quick calculation. So that's nice. So for letter D, they want to know percent yield. Okay, so percent yield. The number that we just calculated over here, this is our theoretical yield. Okay, because again, this is all based on calculations. So, we didn't actually do this in real life. And for letter D, percent yield, we're going to take our actual yield, which in this problem is the 3.99 grams they're giving us, and divide it by the theoretical yield, and then times by 100. So pretty much all we're going to do is we're going to take our actual yield of 3.99 grams, which is what they're giving us in the problem, okay, divided by 4.58 grams. And I'll write the units here so we know what we're talking about. And then times that by 100. Okay, and I know I'm kind of running into my math work here, so I apologize. Hopefully you're following along, but so 3.99 divided by 4.58 times 100, we get a percent yield of 87.1% if we round to 3 significant figures. So 87.1%. That is our percent yield for letter D and the final problem on this review guide. All right, so I know that was a lot of problems, a lot of math work. Hopefully you were able to follow along with me, and all I wanted to do is again make sure that I showed you how to do all these different problems so that you're feeling comfortable and ready for the test. So, all right guys, that is it for this one. As always, if you need any help before you take your test, please reach out to me so that I can help you. You don't want to find out after you've taken your test that you didn't know what you're doing, right? Like, that's not a good thing to do. So, I'm here as always. Thanks for watching, and I'm Mr. B. See you in the next one. Bye.